In today's lesson, we're going to solve quadratic systems. Now, the first type of systems we're going to solve is going to be a combination between linear and quadratics. So we'd have one linear equation and one quadratic equation. The quadratic equation would be any of the conic sections, since they have a degree of 2, hence making them quadratic. Now, we have one of three possibilities when you're dealing with this sort of arrangement. You can either have no solutions where the line or the conic intersect anywhere, one solution where the line and conic or quadratic will intersect in only one spot, or two solutions. So we're going to get one of those three. Now let's look at an example. And we're going to solve a system where we have one line and one conic or quadratic. It doesn't matter. I mean, I can tell that the first one is a line and the second one has a squared. That's going to be the quadratic. But it doesn't really matter as far as what conic it's going to be. We're just trying to find the number of solutions, or what specifically those solutions will be. So the easiest method is to use substitution, just like when we would solve systems of linear equations. So we can simply solve for one of the variables that's not squared and make our life a lot easier. This one's nicely set up because I can see in the second equation that y is already solved for. So I'll just substitute that into the first equation here. So I would rewrite the first one as 2x plus, and then in place of y, I'm just going to put x squared plus 6x plus 7 equals -5. Now it's a good idea to use parentheses here because if this was a minus sign, you'd have to distribute that throughout this expression. But since that's not the case, it's not going to have an effect, but it's still a good practice to put parentheses around anything that you're substituting into an equation. Okay, so now all I'm going to do is solve this quadratic. So I'm going to start off by setting it equal to 0, simplifying and set it equal to 0. So I'll be left with x squared plus 8x plus 12 is equal to 0. And then this factors to x plus 6 times x plus 2 equals 0. And therefore my x value using the zero product property is going to be -2 and -6 respectively. Now that I have my x values of my solutions, I'm going to go forth and solve for my y's, for the coordinates. So I'm going to just substitute these into either one of the original equations. It doesn't matter which. The linear one will probably be the easier one to do, so I'll do that. So I'm going to say 2 times -6 plus y is equal to -5. And that's going to simplify to -12 plus y is equal to -5. So therefore, y is equal to 7. And then I'll do it with the -2. So let's see, that's going to be 2 times -2 plus y is equal to -5. Which is going to leave me with -4 plus y is equal to -5, and y has to equal -1. So therefore my my set of solutions is going to include -6 and 7, as well as -2 and -1. And that's really all I care about when solving, or what the intersection points are. But I'm going to go ahead and graph this just so you can see what this would look like. So let's do that. So this is what it would look like graphically. It's going to be a line going through a parabola at two points. And I can see right here that I have the point -6, 7, and doesn't want to stay there. And the other point is going to be -2, 1, as we can see here. So just like as we did algebraically. Now the next scenario that we want to look at is trying to find solutions to quadratic systems. In this case, we're looking at two quadratics or two conics, and it could be conics of any type. In this case, we have 5 possibilities of having either no solution, 1 solution, 2 solutions, 3 solutions, or 4 solutions is a possibility. And these are all just examples, but this can happen in an infinite number of ways to getting all 5 of these scenarios. So let's look at an example dealing with those. So here's our example with 2 quadratics that we will solve algebraically. Now, when you're dealing with 2 conics, using elimination tends to be the easier method. So we would choose a variable, the easiest variable to eliminate. In this case, since I only have a single y, in case of a y squared, in both equations, I'm going to eliminate that first. I'm going to set this up, though, so that all the like terms are lined up. So it's supposed to be a 16x plus 39 is equal to 0. And then x squared minus y squared. So I don't need to multiply the second one, the second equation, or the first equation by anything like we would do sometimes when we do use elimination, because the signs are already opposite and the coefficients are the same outside of the sign. And so I line up the 9 with the 39, so that when I add these together, I'll be left with 2x squared minus 16. Well, actually the y's cancel out, so let me kind of line this up a little bit better. So the y's end up canceling just like we wanted, then leaving me with minus 16x plus 30 equals 0. Now we just have to solve this quadratic. I can factor out a GCF of 2, leaving me with 2x squared minus 8x plus 15 is equal to 0. And maybe to help avoid confusion, we can divide both sides by 2, just getting rid of that 2 altogether. Or we could have done that from the beginning. But in either case, we would be left with the x squared minus 8x plus 15 equals 0. And this one factors to, let's see, that's going to be x minus 5 and x minus 3 equals 0. So therefore, we would have x equals, using that zero product property again, 3 and 5 would be our two x values. Now, just like the last problem, we can substitute these back into one of the original equations to get our corresponding y values. So I think I'll use the second equation, and we'll start with the 3. So that leaves me with 3 squared minus y squared minus 9 equals 0. In other words, 9 minus y squared minus 9. The 9's end up canceling, um, leaving me with negative y squared equals 0. If we divide both sides by negative 1, we're left with positive y squared equals 0. But it doesn't really matter because y has to equal 0 here regardless. So we know what that first ordered pair is going to be. It's going to be 3, 0. And then we'll do this again with a 5. So we would do, I'll go over here and do this. So I'll have 5 squared minus y squared minus 9 equals 0, which evaluates to 25 minus y squared minus 9 equals 0. And then we can simplify that to negative y squared plus 16 equals 0. Thus, negative y squared is equal to negative 16. Then we'll take care of the negative on the y squared. So we'll divide both sides by negative 1, which will leave us with y squared equals 16. In which quick case then we'll bring in a square root. Since we're bringing it in, we'll have to account for plus and minus. So therefore y is equal to plus or minus 4. Therefore, our solutions in this case will be, we'll have one at 3, 0, and then we'll have 5, and then plus or minus 4, which in this case counts for 2. So we'll have a total of 3 different solutions. Now, let's go ahead and take a look at what this looks like graphically. And as we can see here, we see that there are indeed 3 points being intersected, in this case by a circle and one of the branches of a hyperbola. So we see 3, 0, and then 5, 4, and 5, negative 4. So that's what it would look like graphically. So anyway, that's how you solve quadratic systems. Until next time, I'll see you on the flip side.